Another masked person. Nice.
Not alone.
Hi. Okay.
So Sarah, I believe you are the host of the day.
Yes, I'm just waiting. I was waiting till it struck noon, which it just did. Okay, so I think we're gonna get started, and probably people will trickle in, but I'm just gonna say like an introduction thing anyway. So hello, welcome to the first GOCC of this semester. I'm really glad that you all decided to come back. And yeah, so yes, we're back. Yeah, so before we started, we wanted to just give like a brief community statement that is just the continuation of last year's community statement. But just so that we're all on the same page. So we sort of have three big ideas of the seminar. One is that we're all learning. So even if you're an expert, like a speaker, or if you are a beginning grad student, or maybe you're a professor, we're all learning. I don't want to overlap the next one, which is that everyone has something to contribute. So you can contribute by giving a talk, attending a talk, answering questions, or just like listening. You have something to contribute no matter what level of combinatorics you're at. And then the last one is that no one has all the answers. So and maybe it feels like when you go to seminars, the speakers have all the answers, but we're taking the approach that no one has all of the answers, but we all have some sort of answer to contribute. Okay. So with that, I think we should start. So it's my pleasure to introduce Colleen Robichaux, who will be talking about, let me pull up the title of your talk.
I'll share my screen.
Oh, perfect. Then I can read it off. Okay, Colleen will be talking about degrees of Grothendieck polynomials and CM regularity. Oh, and I'll be monitoring the chat if you want to ask questions via the chat. Yes. All right, take it away.
Great. So today I'm going to talk about some joint work with Jenna Ratchgott and Anna Wygand, in which we are exploring how to compute degrees of Grothendieck polynomials and getting nice combinatorial formulas for those, and connecting these formulas to an algebraic invariant called Castelnuovo-Mumford regularity. And we'll start by talking about Kasdan-Lustig varieties. And these varieties were introduced in 2006 by Alex Wu and Alex Yang in their study of singularities of Schubert varieties. And in studying these singularities, these Kasdan-Lustig varieties naturally arise. And these varieties are these generalized determinantal varieties. So their defining ideals are just certain matrix minors. And just so we're all familiar with this central object of this talk, I want to just go over how you would compute this defining ideal very explicitly through an example. So we'll start with two permutations V and W, where W is always going to be less than or equal to V in Bruhat order. And we'll start by just drawing for W its Rotha diagram. So the Rotha diagram for W, I'm going to start by just looking at W like I have here in one line notation. Oops, my screen froze. I'm going to look. Oops. There we go. Doesn't want to write on the screen.
Now I see it writing, at least.
Yeah, so it always stops after I write one letter, which is unfortunate. I'm going to stop sharing and start again to see if that helps. Otherwise, it'll be No, it's still bad. So I will do my best with minimal writing on the screen. But I start with W in one line notation here, at least that worked. So since 1 gets sent to 4 in the permutation, in row 1, column 4, I'm going to put a bullet there. In since 2 goes to 1, in the second row, first column, I put a bullet, and so on. So 3 goes to 3, row 3, column 3, 4 goes to 2, row 4, column 2. And then south and east of each of these bullets, I'm going to X out all of that space with these sort of rays that are going south and east of each of these bullets. And then in this 4x4 grid that we're working on top of, any integer point that hasn't been already occupied, I'm going to draw a box in those locations. So that's what these boxes are the sort of leftover locations after this process. And this box is precisely the Rotha diagram for W. That's that collection of boxes. And so from this Rotha diagram, what I'm going to do is I'm going to compute the rank matrix of my permutation. You can compute this a lot of different ways, but how you can think about computing it is for a position in your rank matrix, how you compute what number you would fill there is you go to the sort of corresponding location in your Rotha diagram, this grid sort of diagram. And when you're at this position, you ask yourself, if I'm looking northwest, how many of those bullets am I going to see if I'm standing right here? And you would see 2, so you're going to record a 2 here. Whereas if I was maybe here, you would see just this bullet when you look northwest, so you'll store a 1 in that location. And that's how you get your rank matrix. And this rank matrix is going to tell us what size minors we're going to be taking to get our generators for this defining ideal. So this defining ideal is generated by these certain minors, and the minors are dictated by this. And how we figure out what matrix we're going to be taking these minors of is basically just the Rotha diagram for V instead. So somehow the Rotha diagram for V is hiding inside of this matrix, where everywhere that I would have had a bullet, I've put a 1 instead. Everywhere that would have had one of those rays gets a 0. And all of my Rotha diagram boxes gets these indeterminates Zij. And so by taking minors of this matrix, this is how I'm going to get my generators for this ideal. So for my minors, what I do is I'm going to take sort of northwest minors. So I'll choose a lower corner of the matrix I want to take minors of. So let's say I'll take that lower corner for my matrix, my submatrix. And according to the definition of this variety, I want to take the minors of this northwest matrix. And the size of minors is I look at the corresponding position in the rank matrix of W. And that tells me I want to take it stores a 1, so I want to take the 1 plus 1 size minors of this matrix. So I always do this, whatever the location is, plus 1 size minors. And so all in all, that would tell me that I want to take the 2 minors of this submatrix. So for example, one of the generators for my ideal would be this minor here. So Z11 minus Z21, Z12, which appears right here as a generator. And then another example, I could choose this corner from my matrix. I would take the northwest submatrix that corner defines. And how I decide what size minors I take is I look at the corresponding position in my rank matrix, and I take that number plus 1 size minors of this submatrix. So here I would just be taking the 1 minors of this submatrix. So that would give me each of these generators here, right? And I can do that for every single position in this matrix here. I can pick a corner, figure out what size minors I should be taking, and add that to my big list of generators. But one thing that's particularly nice about these varieties is, according to a theorem of Fulton that was later generalized, is we can actually be pretty lazy about which matrices we're bothering to take minors of. And this theorem says that we can only bother taking corners that correspond to particular corners of the Rotha diagram. that correspond to the essential boxes of the Roth diagram, if you're familiar with those. But all you need to know is, there's a nice way to be a bit more lazy about how many generators we're bothering to compute. All right, so this is how we get our defining ideal for our variety. And one nice thing about these Kasdan-Lustig varieties is they contain lots of nice families of other determinantal varieties, generalized determinantal varieties. So if you've ever heard of matrix Schubert varieties, they're defined in precisely the same way as these Kasdan-Lustig varieties, except the only difference is you do the same business with the rank matrix. The only difference is instead of taking your minors of this matrix of these indeterminates with zeros and ones, the matrix you're going to take your minors of is just going to be all Zij's in the case of matrix Schubert varieties. So it's a bit easier. So you can think that to get from a matrix Schubert variety to a Kasdan-Lustig variety, you're just going to set some of your variables equal to 0 or 1, and that's how you can move between. But in general, these matrix Schubert varieties are special cases of these Kasdan-Lustig varieties. And additionally, the classical determinantal varieties are examples of matrix Schubert varieties. So for example, if you just have a rectangular matrix of indeterminates and you say you want all of the 3 minors of that matrix, that would be giving you a classical determinantal variety. So this class of varieties contains lots of nice examples that we might want to look at. And these Kasdan-Lustig varieties have the extra plus that they have this cool connection to the singularities of Schubert varieties. So maybe we want to think about other invariants of these varieties and think about them more algebraically, see what that can tell us. Well, what we can do is we can look at its minimal free resolution. So when we have a coordinate ring here, we can build this minimal free resolution of free S modules here. And how you build this is it sort of has to do with the relations between the generators of your coordinate ring. That's how you're sort of building this out. I'm not going to get into the details of these minimal free resolutions, and sort of the whole point of this talk is sort of being able to sidestep the minimal free resolutions, but it tells you about sort of how complex the relations between these generators are, looking at this minimal free resolution. And so from this resolution, you can get your K polynomial, where this is built from these graded Betty numbers, which is telling you sort of about the multiplicities of these free S modules here. And so the K polynomial is some polynomial where the coefficients are some alternating sum of these Betty numbers. And we can also get from this minimal free resolution the invariant of Castelnuovo-Mumford regularity of our coordinate ring, which is again a statistic on the non-zero Betty numbers, where it's just trying to capture what is the biggest difference of the indices of these Betty numbers. And all in all, what this regularity is measuring is giving you some sort of rough estimate as to how complicated the minimal free resolution is, how complicated, how messy maybe this coordinate ring is that you're trying to work with. And if you're trying to approach something, you might want to know how nasty it is before you go on working with it. So maybe you'd like to have an easy way to compute this regularity to get this rough check on how gross it's going to be to work with. But if you don't know how gross it is to work with, maybe you don't want to go about computing the minimal free resolution to get that answer. Maybe you want something a bit easier, is an easier way to compute that. And in the case of Cohen-Macaulay coordinate rings, we actually have a nicer way to potentially compute this regularity. So we can, when we're in that Cohen-Macaulay case, our regularity is going to be the degree of this K polynomial. And a lot of these K polynomials have nice combinatorial definitions that we'll talk about. And you just subtract off the codimension of your ideal, and that's how you can also compute this regularity. All right, so let's see what we can do with this and get into some more combinatorics, what we're all here for. So as I mentioned, these matrix Schubert varieties are particularly nice cases of these Kasdan-Lustig varieties. And we actually know a lot about matrix Schubert varieties. So due to work of Knudsen-Miller, we know that these matrix Schubert varieties are Cohen-Macaulay, so they're pretty well behaved. And we know that their K polynomials are these Grothendieck polynomials that I'll talk about in more detail in a couple of slides. And then due to Fulton's work, where he introduces matrix Schubert varieties, he tells us that the codimension of the defining ideals for matrix Schubert varieties is precisely the Coxeter length of the permutation you're working with. So that codimension is just that number of inversions in your permutation. All right, and then if we just connect all of those facts with the theorem I presented on the previous slide, we have that the regularity of these matrix Schubert varieties can be computed by just taking the degree of that Grothendieck polynomial and subtracting off that Coxeter length. And we can more easily get this read on how complicated these defining ideals are, how complicated these coordinate rings are, which sounds great. Now, when we think about doing this in practice, I mean, it's easy to compute the Coxeter length of a permutation. You know, it's easy to sit down and write down all the inversions if you want, or another way that you can count the Coxeter length, it's also the number of boxes in your Rotha diagram as well. So we have a lot of great ways to compute that Coxeter length. What about this degree for the Grothendieck polynomial? That's our next roadblock to getting these regularity formulas. So when we originally started talking about this question, there weren't any easily computable formulas for these degrees. There are certainly there are formulas that you can compute these polynomials combinatorially, but we wanted easy formulas for the degrees. But with work of myself, Jenna Rajkot, and Anna Wygant, we were able to get partial results for this case that I'll present. And then later work of Oliver Pechenik, David Spire, and Anna Wygant completely answers this question, which is fantastic. And so to make sure that we all understand what Grothendieck polynomials are, because maybe you don't see them every day like me, we're going to introduce them by first talking about a sort of simpler polynomial called Schubert polynomials. And Schubert polynomials, they pop up in the study of the cohomology of the complete flag variety. But today, all we need to know is they have this nice combinatorial definition. And they are also pop up in connection to matrix Schubert varieties, as they are the multi-degree of matrix Schubert varieties. And how that relates to our present discussion is the multi-degree is going to be the lowest degree terms of your K polynomial. So the Schubert polynomial is going to tell us what the lowest degree terms of our Grothendieck polynomials are going to be. So what are the degrees of Schubert polynomials? Well, looking at combinatorial formulas that we have at hand due to Fomin Kirillov, Billy Jakush Stanley, and Bajorabili, we can get a good handle on what those degrees are. So how we can compute these Schubert polynomials is we can take this Rotha diagram that we have seen before and we'll see again for our permutation W here, so 1, 3, 2. And everywhere that I see a Rotha diagram box, I'm just going to put a plus there. And then I'm going to just left align all the pluses and forget all of those death rays and bullets so that I just see, this plus and this 3 by 3 grid left aligned in that second row. And what Bajorabili did was they showed us that from this special sort of bottom guy, what we can do is generate all of the possible other diagrams that we can compute our Schubert polynomial from. And so what they say is you can do certain local moves to get all of the possible diagrams. And the local move is if you have a plus all alone in this lower left-hand corner of a local 2 by 2 subsquare where all of these other boxes are empty, you can just have it hop diagonally up like that. And so you can see that's exactly what's being done here. You have this subsquare where you have this plus in this corner, and it hops up like this. And there's also another sort of generalization of this rule where you have pluses that can sort of hop across. These are called ladder moves, but for now, all you need to know is you have these little simple moves with pluses And that's how we can compute all of what are called reduced pipe dreams. And so you can see if you try to do any other moves, any other of these moves, you're not really going to be able to generate anything else to compute your other reduced pipe dreams. So these are all of our reduced pipe dreams. And how we get our Schubert polynomial from this is we just think about all of the row indices that these pluses are appearing in our pipe dream, and that will tell us a monomial that's going to contribute to our Schubert polynomial. So this diagram, we have a 1 plus in row 1, that's going to give me an x1. And in this diagram, we have a plus, 1 plus in row 2, so that's going to give me an x2. And that's all of our pipe dreams, so that's going to be all of our monomials. All right.
Quick question.
Mhm.
Does the number of pluses in the row matter? So if I had 2 pluses in a row, would I get
Right,
it?
so yeah, so if you had something like that, so 2 pluses in row 2, that would give me an x2 squared. In that
Okay.
case. Yeah. Excellent question. All right, and so when we're thinking about what the degrees of these Schubert polynomials are going to be, this is exactly, I think, touching on what Mark was sort of getting at, is the degree of your Schubert polynomial is going to be exactly that number of pluses that you have going on in your pipe dream. And so since we're building this original pipe dream from the Rotha diagram, the degree is going to be the same as the number of boxes in your Rotha diagram, which is exactly that Coxeter length. So we have an excellent understanding of what the degree of the Schubert polynomial is. That's just that Coxeter length, which tells us that we know that the lowest degree terms of my Grothendieck polynomial are going to be precisely just that Coxeter length. So I've talked Schubert polynomials to death. What about these Grothendieck polynomials? Now these Grothendieck polynomials pop up in the study of the K-theory of the complete flag variety. It gets a bit more complicated. But you can compute them in a really similar way to the Schubert polynomials. So just like Schubert polynomials, you start with a nice sort of base case where you know what the Schubert and Grothendieck polynomials are for the long word. And then by recursively applying certain divided difference operators, you can get any polynomial that you want for whatever permutation you're indexing by. But as we remember, the Schubert polynomials are going to be the lowest degree terms. But in general, unless you're just that long word here, the Grothendieck polynomials will be in general inhomogeneous. So often you will have higher degree terms popping up. And we can see that combinatorially due to a formula due to Fomin and Kirillov for Grothendieck polynomials. And what their formula tells us is we start off in a very similar way to the case where we were generating Schubert polynomials. And here we're going to call these figures rather than reduced pipe dreams, we'll just call them pipe dreams. But we start with, again, the Rotha diagram for W. We make each box a plus and left align it to get this special bottom one. And then the moves that we're allowed to make in any local 2x2 subsquare is we can do the old reliable of just moving the plus across diagonally, but we can also sort of leave our mark behind us. So in sort of, what is that called? Where a cell can, become two. So it can sort of make two of itself and leave one copy where it was and then move an extra copy across. And so this is exactly telling us mitosis, yes. So it's sort of like that where you can have an extra copy, exactly. Thank you, that was gonna bother me for all of the talk. So we can have, this splitting is exactly exhibiting the fact that we can have these higher degrees because again, the degree of these polynomials is gonna be the biggest number of pluses we can possibly have in these diagrams. And so we can do all of these possible moves with that extra fancy ladder move also factored in, but it's not coming into play here. And we do all those possible moves. So in this 2x2 subsquare, you can see an example of each of these moves being done. And we can get our polynomial from each of these monomials from each of these diagrams. So this is giving us an x2, this is giving us an x1, and this is giving us an x1, x2. Right? So this is showing us that, again, that degree is precisely the biggest number of pluses we could possibly stuff in these diagrams, which doesn't sound that hard. If we look at a bigger example, we again start with the Rotha diagram, put the pluses in the boxes, left align them, and let's see what happens when we try to move pluses. As we can start, let's maybe try to move this plus diagonally. So let's just move that one, not doing a fancy move or anything. Let's see, I'll make that one black. And then we can do some of these almost like mitosis moves. Although I hesitate to say mitosis because mitosis is, it is an actual thing with ordinary pipe dreams due to Knudsen-Miller. So we can move these pluses and have this sort of multiplicity popping up. So we can get 3 extra pluses if I did it this way to get this pipe dream that I have here, doing these sort of local moves in these subsquares. And when we're thinking about how you would compute the degree, you have to figure out the most of these extra pluses that you could possibly have popping up. But it's hard to know for sure that you made the right choices along the way, that you were able to actually maximize things in the way that you wanted. So while you can use this formula or this rule for Grothendieck polynomials to compute that degree, it's hard to be really confident that you actually know what the degree is and that you didn't just miss the right one that actually gives you the highest degree. So we were on the hunt for a more succinct formula to be able to compute that degree that has less room for error. And that's what we did for the case of vexillary permutations. So a vexillary permutation is just a permutation that avoids the pattern 2, 1, 4, 3. So for example, an example of a permutation that's not 2, 1, 4, 3 avoiding would be like, well, let's see. So this would not be 2, 1, 4, 3 avoiding because this would be sort of forming a 2, 1, 4, 3 pattern, where that's sort of the relative order between the entries. Okay, so for the permutations V that are 2, 1, 4, 3 avoiding, myself, Jen Ratchgott, and Anna Wygant have an easier way to compute those degrees. And I'm just going to go through what this formula means, again, through an example, because it looks a bit overly complicated just looking at the theorem statement. So we'll start by just looking at our permutation in one-line notation here. So 1, 2, 5. I'm glad my pen got working again. And we'll start, as we always do, by drawing out the Rotha diagram for our permutation. And we're going to fill each Rotha diagram box with the rank. So just like how we were computing the rank matrix earlier on the first slide to define that Kasdan-Lustig polynomial, we're going to compute that here, but we only care about filling it in the places that actually have a Rotha diagram box. So like here, it gets a 1 because it sees 1 bullet, as a reminder. And to compute this value for our theorem, I like tableaux, so I want to turn this into a tableau. So we're just going to shove all of these boxes as northwest as possible to get a nice little tableau. That'll be easier for us to work with. And what our formula says is that we're just going to take first that Coxeter length, or that number of boxes in my Rotha diagram, which here is just 12. And then I'm going to go through this process to compute this extra stuff that I'm tacking on to the end. And to do that, I'm going to go through the integers 1 to n. So in this case, 1 to 7. And it's just a simple process that we'll go through. So we'll start with I equals 1. And for that, we're just going to look at the subset of my tableau that has entry greater than or equal to 1. Easy enough. And then for each of those connected components, I want to look at the biggest anti-diagonal that I can see inside of each shape. So here I just highlighted the two longest anti-diagonals. This one is length 2, so that's going to give me a 2. This one is length 1, it's going to give me a 1. And now I'm done with I equals 1 and move on to I equals 2. So I look at the subset of my tableau that has entry greater than or equal to 2. So that's just this one box. The biggest diagonal is just that one box. So that's going to give me a 1. And then if we do this for 3, that's going to be nothing. We don't have anything in our tableau that's greater than or equal to 3. So that tells us we're actually finished. So that extra stuff that we're tacking on to that Coxeter length is just 4 to give us that our final degree is 16 in this case. And in case anyone is curious about what our intuition was in computing this formula, we were sort of inspired by the formula for Grothendieck polynomials indexed by vexillary permutations given by Knudsen, Miller, Young. And in their formula, they give these Grothendieck polynomials in terms of these flagged set valued tableau. So I love tableau, so I think this rule is great. You have that you generate a certain set of tableau, and the entries of that tableau are telling you about the monomials of this vexillary Grothendieck polynomial. And in this formula, from your vexillary permutation, you extract a partition, which gives you the shape of this tableau that they're using. And based on sort of the ranks of certain boxes, you're getting some bounds on how big entries can get in each row of the tableau. And so that's giving a sort of flagging condition on each row, how big entries in each row can get. And these tableau that they define are also so-called set valued. So you can have more than one entry in each box, as long as when you read across rows, you're weakly increasing, and down columns, you're strictly increasing. And so with all of those pieces in mind, using their formula, the degree of this vexillary Grothendieck polynomial is the most number of entries you can possibly stuff into these tableau, because the monomials are just recording how many of each number you used in your tableau. And so when we were looking at these tableau and how you can stuff the most entries as possible, it's maximized whenever you're looking at these anti-diagonals inside of these shapes. So that was sort of the secret sauce to the theorem. It wasn't how we actually proved the theorem, but it was very helpful in us getting this conjecture that we were able to prove. Right, so as I mentioned, we had that theorem for our degrees of vexillary Grothendieck polynomials. And as we saw, we had that Coxeter length already hiding inside of that theorem that was computing this degree of this polynomial. So because our regularity, we know that's equal to the degree of the K polynomial minus that codimension, we have that our regularity is actually just going to be that extra stuff that we were computing all along. So turning back to that original example that we were looking at, we found that that extra stuff added up to 4. So our regularity in that case is just 4. Easy. And now I'm going to sort of shift to, instead of just talking about Schubert varieties, we're going to take a step back and go back to talking about Kasdan-Lustig varieties a little bit. And most of the Kasdan-Lustig varieties we'll talk about are going to be indexed by Grassmannian permutations. So these Grassmannian permutations are those that when you write them in one-line notation, you have what they call a unique descent. So your entries will be increasing, increasing, decreasing, and then increasing, increasing the rest of the way. And one really nice thing about Grassmannian permutations is once you've decided which symmetric group it's living inside of, you can uniquely associate it to a particular integer partition. So for example, we would just cut off the first part of the permutation before that descent, and then draw boxes 2, 4, 8, cut out a little staircase, and that's going to give us the partition that we will uniquely associate to this Grassmannian permutation. And so now that we know this sort of relationship between Grassmannian permutations and partitions, that'll help us with our theorem. So in fact, these Kasdan-Lustig ideals, or these Kasdan-Lustig varieties that are indexed by these Grassmannian pairs, where the pairs that we're going to be talking about, we're only going to consider pairs that have the same descent, or in other words, the partitions that they're associated to are going to have the same length. But whenever we have this relationship for this Grassmannian pair, in fact, these Kasdan-Lustig varieties are going to be precisely isomorphic to vexillary matrix Schubert varieties. And so because these are invariants, the regularities will also be the same. And using our theorem, we can now easily compute the regularities for Kasdan-Lustig varieties indexed by these Grassmannian pairs. But of course, one thing to keep in mind is I say that we have this relationship between this Grassmannian pair and this vexillary matrix Schubert variety, but for practical purposes, it's not going to be very helpful if this map isn't very easy to describe. But luckily it is. So I'm just going to sort of outline how that works because I think it's neat. It involves the combinatorics of excited Young diagrams, if you're familiar with those. But to do this, we start with our Grassmannian pair here. And I just care about what the partitions that are associated to these Grassmannian permutations are. And I'm going to draw U sitting inside of W here, based on the sort of relationship between U and W that I am assuming due to this Kasdan-Lustig land. That'll always work. I'll always be able to write the partition for U inside of W. And all I'm going to do is, again, for each 2x2 subsquare, I have this local move where I can move the shaded boxes down diagonally, according to this, whenever these are all empty. Okay, and so what I want to do is, restricted to the game board that is the partition of W, I want to do as many of these moves as possible to slide these shaded boxes as southeast as I can. And when we do that, we will actually just see the Rotha diagram for V hanging out for us to read off. So luckily, once we have this U and W, we compute the partitions that they're associated to, do these sort of trickling moves southeast, and then we can just read off the Rotha diagram for V and apply our theorem. So in this case, the V that these are associated to is precisely the same one that I've been using in all of my examples. So the regularity of this Grassmannian Kasdan-Lustig is just 4. And we can apply this theorem in a couple of different settings. So the first that I'll talk about is in relation to a conjecture of Kumini Lakshmibai Shastri Shashadri, in which in their paper, they were exploring the free resolutions of particular open patches of certain Grassmannian Schubert varieties. And at the end of their paper, they had a conjecture about their Castelnuovo-Mumford regularities, where the permutations that they were considering, they did have some certain conditions on the W's, but I won't get into too much details with what those conditions exactly were. But what their conjecture says is for those Grassmannian partitions that they were considering, they conjectured that you were able to compute those regularities by just taking some weighted sums on the differences of consecutive entries in that partition. So they had this really cute formula to really easily compute this regularity. But what was nice for us is, in fact, these open patches of these Grassmannian Schubert varieties that they were considering were actually Kasdan-Lustig varieties. And not only were they Kasdan-Lustig varieties, they were Kasdan-Lustig varieties indexed by a pair of Grassmannian permutations that in fact just reduced to just the regularity of that Grassmannian matrix Schubert variety, which was fantastic. So then we were really excited when we saw that this was the case, because if you are a vexillary permutation, if you're a Grassmannian permutation, you're a vexillary permutation. So our formula applies to potentially either prove this theorem or give a correction, or either prove this conjecture or correct it. So let's see in an example how these compare in practice. So we can take our Grassmannian permutation here. I've drawn out its Rotha diagram. And if we apply our theorem, you just write down the ranks here. So those are the ranks if you look at the bullets here. It's super easy in the Grassmannian case. And you shove all those boxes northwest. And then if we are applying our theorem, for I equals 1, we have an anti-diagonal of size 3, gives us a 3. And then we look at the subset greater than or equal to 2, that's just this box. For 2 and 3, and both times the anti-diagonal is just size 1. So we can quickly compute that in this case, the regularity should be 5. And if we look at this permutation, it's not too hard to read off that the corresponding integer partition that we associate with it is 3, 2, 2, 0, which you're also able to read off from the Rotha diagram. If you're sort of reading bottom up, the number of boxes in each row is another way to tell what the associated partition is. There's 3 boxes, 2, 2, 0. But applying their theorem to this case, we have this weighted sum. So 1 times the difference between these 2 entries, 2 times the difference between these 2, and 3 times the difference between these 2 entries. So their conjecture would tell us that the regularity is 7, but it's 5. So we now know that their conjecture does not always hold, and we're able to correct it. One interesting thing is before this project for vexillary matrix Schubert varieties, I had a previous project with Yiren Janarachkat, Avery Saint-Dizier, and Anna Wygant, in which we proved it for the Grassmannian case. And in that case, it's really easy to see when our formula is actually matching the conjectured formula of Kumini Lakshmi by Shastri Shashadri. The second application of our theorem for Grassmannian pairs applies to these one-sided mixed ladder determinantal ideals. It's very wordy. But how you define these ideals is you start with, instead of the classical determinantal case where you're just taking your minors of a rectangle of indeterminates, you're instead just going to have your indeterminates living in sort of a partition shape where you're not going to take any minors out here. And so you have this sort of crumpled side of your rectangle. So that's sort of what that one-sided is talking about. And what this mixed is coming from is you're determining what size your minors are going to be by these sort of marked points on this edge, where if you have, like, let's say a 3 at this point here, this would tell us that of this matrix of indeterminates, you're going to take the 3 minors in this northwest region. Or if you had a 4 over here, this would tell you to take, the 4 minors over here. So that's where this mixed is coming from. And in fact, these are, again, Kasdan-Lustig varieties. There are Kasdan-Lustig varieties indexed by this Grassmannian pair, which we know are isomorphic to vexillary matrix Schubert varieties. So it's been known that these one-sided mixed ladder determinantal ideals were in fact vexillary matrix Schubert varieties. And of course, this means that we can apply our theorem. So as a corollary, we can also compute the regularities for these one-sided mixed ladder determinantal ideals. And then the last thing I will talk about is some future work where I try to sort of extend what we've been doing to two-sided mixed ladder determinantal ideals. And so the two-sided means I'm not only crumpling this edge, but I'm also crumpling the top edge. So I'm taking my minors of sort of a skew shape of indeterminates. That's what I'm taking my minors of. And one nice thing about these two-sided mixed-ladder determinantal ideals is they're again these Kasdan-Lustig varieties, but now these varieties are indexed by a pair of 3, 2, 1 avoiding permutations. So we're not in that nice Grossmanian case anymore, but 3, 2, 1 avoiding permutations are also fairly nice. With Jenna Rajgan and Anna Wygant, we have formulas for matrix Schubert varieties indexed by 3, 2, 1 avoiding permutations. So it seems like we might be able to get a handle on these Kasdan-Lustigs that are indexed by 3, 2, 1 avoiding permutations. And what that sort of will involve is looking at the K polynomials of these Kasdan-Lustig varieties. So before I mentioned that the K polynomials of matrix Schubert varieties were ordinary Grothendieck polynomials, whereas now if we look at the K polynomials of Kasdan-Lustig varieties, these are now going to be these so-called unspecialized Grothendieck polynomials of Wu and Yang. And how you compute these is very similar to the case of our ordinary Grothendieck polynomials, where you have this is our Rotha diagram for W. And here I've drawn out all of those pipe dreams for W that we had before that were defining our ordinary Grothendieck polynomial. But for this unspecialized Grothendieck polynomial, I put an extra condition on the pipe dreams that I'm going to allow. And how we sort of have that condition is I have the Rotha diagram for V here. And so I have 2 boxes in the first row. So this is going to sort of give me a sort of game board that I'm going to restrict my pipe dreams to live on top of. And so that's what these shaded boxes are representing. And so for these unspecialized Grothendieck polynomials, I'm only going to allow the pipe dreams that live inside of this shaded game board. So what this would tell me is, according to the definition given by Wu and Yang, the unspecialized Grothendieck polynomial would only be generated by this singular pipe dream here, because this is the only option that I have where all of the pluses are sitting inside of this shaded region. So in this case, the unspecialized Grothendieck would just be X1 because there's just a plus in that top row. So hopefully by studying these unspecialized Grothendieck's, we can get a nice formula for this 3, 2, 1, 3, 2, 1 avoiding case. And in closing, just to summarize what we've talked about today, we can express this invariant of Castelnuovo-Mumford regularity for matrix Schubert varieties in terms of the degree of its K polynomial, which is the Grothendieck polynomial, subtracting off that codimension, which is that Coxeter length, that inversion number of your permutation. And in the case of vexillary matrix Schubert varieties, we have an easily computable formula inspired by this Knudsen-Miller-Yang flag set valued tableau rule to get our regularities. And by connecting Grassmannian Kasdan-Lustig varieties to these matrix Schubert varieties in the vexillary case, we can correct a conjecture given by Kumini, Lakshmi, Shastri, Shashadri, and get formulas for these one-sided ladder determinantal ideals. I'll stop there. Thank you.
Awesome. Let's all thank Colleen by either clapping in the chat, or you can unmute and clap yourself. That was a great talk. Cool. So does anyone have questions?
So I have a question. So you corrected the KLSS formula, but so I mean you gave us one example of where it's wrong, and I noticed it is now an upper bound. So does the formula miss on both sides? Can it be used to bound the regularity?
I think it is an upper bound in general. Yeah, so it is still useful in that case because it is super easy to compute using that formula. So it was interesting in comparing to that previous paper of ours that we mentioned. It was clear that It's sort of just a bit of an overestimate in general.
All right.
References. So our paper is not yet on the archive, but my paper with, let's see, with Avery, you can also email me and I can send you things, but let's see. I will try to put our previous paper in the chat. And that has a lot of the references that we were using, but with regards to the cosmoleustics and things, that should be out hopefully in the next couple of weeks. This paper that I was talking about.
I had another question. So these vexillary permutations, they are 2, 1, 4, 3 avoiding, but they're not 3, 4, 1, 2 avoiding.
Right. So these are permutations where there's a nice description where if you are connecting all of the essential boxes of your permutation, it's on a northeast oriented curve.
Okay.
That's one of the best ways that I know how to describe it visually. I don't think I ever defined earlier what an essential box is, but those are just the boxes in your Rotha diagram where there's no box here, there's no box here, in sort of corner.
I've been working with separable permutations recently, so I'm like, oh, that's halfway there.
Yeah. Yeah, so often with these pattern avoidance things, you can get some nice families of things you can really get a hold on for these formulas.
And so this might be a hard question, but do you know what it is about 2, 1, 4, 3 avoiding that makes it easier to come up with a degree for the Grothendieck polynomial?
So
Or like, what is it about them that makes this work? Or yeah.
One particularly nice thing is there's this recursive formula you can use to compute Grothendieck and Schubert polynomials called transition. And that's a way to recursively compute these where you'll have, this Grothendieck is this Grothendieck plus monomial times other Grothendieck's. And in the case when you're vexillary, this formula is a lot simpler than in other cases. So that's one reason that there's been a lot more development in these formulas because transition is a particularly powerful tool to get a hold of. That's how we proved our formula, for example. But even in Fulton's seminal paper on matrix Schubert varieties, he picks out that these vexillary ones are particularly nice.
Cool, thanks.
All right, last call for more questions. Okay, let's thank the speaker again for a great talk.
Yeah, thank you for having me.
Yeah, that's an excellent way to kick off the seminar. So I think next week we're meeting on Tuesday instead of Wednesday. So it'll be like slightly irregular and then we'll be back to Wednesdays. So hopefully you can all make it for the weird day or for the rest of the semester.